over 6 is all about probability. Now, probability is a very deep and complicated concept. Of course, we don't care about that much. It's just going to be the very first little bit. And that is when we have what we call equally likely outcomes. Equally likely outcomes. A simple situation is, for example, it's just an example, there's no number. Example. I'm going to roll, let's make it easier. Let's say I'm rolling 1 balanced, I guess, 6-sided die. That means any number, the numbers 1, 2, 3, 4, 5, 6 are the possible outcomes and all equally likely. There's no bias, there's nothing. If I roll, I can get a 1 just as likely as a 3, just as likely as any other number. So dice situations are nice to think about in this setting. If I then ask, what is the probability of getting 2? What would you say? The probability is an attempt at using a number to represent how likely something is to happen. And hopefully we all say, well, it's a 1 in 6 chance. So the probability is going to be a fraction, 1 over 6. If, for example, I say the probability of getting, that was an I, getting an even number, what would you say that is?
3 over 6.
3 over 6, 1 and 2, because half of them have the property that I'm looking for. So, in this elementary level, it's as simple as looking at the number of outcomes that we want, that we're interested in, over the total number of outcomes. And yes, then you have a fraction. Sometimes you can simplify that fraction, sometimes you can't. Doesn't really matter. So that number, that fraction, gives you an idea of how likely this is to happen. So getting just a 2 is of course less likely than relaxing my requirement and just getting even numbers. We can make it a little more interesting, I suppose. If I relate it to the book, I could say, well, let's roll 2 dice. Still balanced, 6-sided. 2 dice. And then we have a lot of options. Let's pretend one is red and one is blue. Just going to make things easier. Then I can get a red result, which is not the full outcome because I rolled 2. I can get that in 6 ways. I can get a blue number in 6 ways. So that means that the total number of outcomes, an outcome is now a pair of numbers. There's a first and a second, a red and a blue, or whatever. How many would you say, how many ways can I get a result? How many different results can I get? Not 12, it's 36, it's multiplicative. Because if you think of the red sort of happening first, let's pretend we're rolling them one at a time. I have 6 possibilities, 1, 2, 3, 4, 5, and 6. For each one of those, it could be linked with 6 possibilities in the blue. So I have 6 groups of 6, which means multiplication. I think I made too many little marks to backtrack everything. See how far I can get. Oh, so close. Oh, that's as far as I can get. Is everyone happy with 6 times 6? I sort of visualize that tree branching off more and more options. So it's 36. Now these aren't going to get super complicated for us, but so if I now say, let's suppose I'm interested in rolling 2 of the same number. A little more mathematical and less words, we can define a set or an event. Let E represent the event of desirable outcomes. In this case, let's say, for example, the event that we get the same number. And the red and the blue. A double. A double. 2 1s, 2 2s, 2 3s, and so on. Then the probability we're going to write as the P for probability, and then the name of the event. And all it does is it's just trying to save me from writing all the words. It doesn't change the meaning at all. I could have written the words, probability of getting 2 of the same number. Just trying to make it a little bit more compact and efficient. What would you say is the probability of getting 2 of the same number? Without simplifying. Well, how many ways can I get 2 of the same number?
6.
There are going to be 6 doubles. Which word are you looking for? This one? I'm guessing, I don't know which one you're looking for. 6 ways of getting a double over a total of 36. Yes, that simplifies. I don't really care. Because sometimes it will, sometimes it won't. There's a 6 in 36 chance of getting what I want. So the concept of a probability is hopefully not too complicated, and we certainly don't want to make it complicated. What we do want to do, perhaps, is make it a little bit more presentable by converting these to percentages. How do I convert a fraction to a percentage? No eye contact. Don't look at me. I multiply by 100. What do I get when I take 6 divided by 36 times 100? Let's say 2 decimal places.
0.1667.
I think that was cheating, but all right, I'll take it. Okay, what do I do? Oh, it's the same. It's not very exciting. Here, this one. What is this percentage? 3 over 6. This is 50%. So by making it a percentage, it's just easier to present. It's a more presentable probability. And it's more comparable across different situations. They're all percentages. Even though the fraction might look different, people don't like comparing fractions with different denominators. But comparing percentages, it's much more immediate to know which one's more likely and which one's less likely. So I could say, for example, it's more likely to get even number if I roll 1 die versus getting a double if I roll 2. Because I just compare those percentages. So it's much more straightforward. You multiply by 100. The probability, the fraction. So I just want to interpret this percentage. Let's take this last one. So it gives you an indication, depending on where it sits, 0 to 100%. Closer to 0 means less likely that if I were to do this once, I'm probably not going to expect to get a double. It's possible, I can get lucky, but probably not. Whereas if that percentage was, let's say, 90 or something, that gives me a lot more confidence that, yeah, I'm not guaranteed. But if I were to do this once, I might get it. It's a good chance. So where it sits from 0 to 100 is an indication of how likely it is, or what I could expect, 0% to 100%. What I could expect if I do it once. This guy sits over here somewhere. Not great. It's a little closer to 0. Another interpretation is, I'll write this down, if we repeat this experiment, the experiment is rolling 2 dice many, many times. It has to be many times, because if I roll 2 dice right now, I can get a double. Maybe I roll it again. I can get a double again. Just be very lucky. And it could give me a false impression of how likely this outcome is, or this event rather. But if I were to repeat it many times, it'll stabilize. If I repeat this experiment many times, we will get event E, which is getting a double, approximately 16.67% of the time. So if I were to repeat this experiment, let's say 1,000 times, I roll, I see what I get. I roll, I see what I get. Around 16% of that 1,000, so around 160, will be a double, and the others will not. Different ways of really saying the same thing. What does this percentage, what does this probability number tell me? It's supposed to tell me something, or what's the point? It's trying to give me, by way of a single number, an impression of what I can expect if I were to actually do this. Any questions on the basic probability concept? And we're not going to do much more with that kind of calculation. Just a fraction of looking what I'm interested in over all possibilities. Any thoughts? Yeah.
I'm just wondering how you got the 6 over 36.
I'm counting, so I need to know what am I interested in. I'm interested in getting the same number among the 2 dice. So then I count. How many ways can I get that? It could be 2 1s, 2 2s, 2 3s, 2 4s, 2 5s, 2 6s. There are only 6 pairs over a total of 36. So I'm literally, often for dice questions at this level, I just list them all and count them one by one. There's no shortcut needed because there aren't that many of them.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.